we're asked to consider the function given, and then determine the intervals of increase and decrease, and then we're going to determine where the curve is concave up and down. We're going to find our inflection point or points, and then we're going to sketch the graph. So let's find our intervals of increase and decrease first. So what are we after here? Well, we're going to want to find the first derivative, right? Because if you remember what the first derivative is, it's the slope. So we're going to find the areas where the slope is positive, right? Because that would be a positive or an increase area. So if you can imagine, if you had a section like this, it's a positive slope. So that means our graph's going to be increasing. Yeah. Or if, it came down like this, then it's going to be decreasing. All right. So let's first find the first derivative. So first derivative. All right. So this should be pretty simple or pretty straightforward because we just have individual terms set up. So our first derivative, so y prime, would be 3x squared minus 6x and then plus 4. Okay. So yeah, that didn't take much time at all, right? So now from here, we want to figure out, well, where is this equal to 0? Okay, because 3x squared minus 6x plus 4, where this is equal to 0, those would be our critical numbers. This would be where our graph actually changed from increasing, something like this, to decreasing. So probably like a max or a min or something, right? So that's why we're setting it to 0. We want to know when does that happen. All right, so what you would typically do here is you just factor it, but it turns out that this one is in fact, you can't factor this. So from there, what we're going to do is we are going to use the quadratic formula. So if you remember the quadratic formula, it is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we fill this in with, this being a, b, and c, so x is equal to, so this is negative, and then in brackets negative 6 plus or minus the square root of, and then negative 6 squared minus 4 a, so our a value was 3 and our c was 4 all over 2 times 3. So now let's simplify this up a little bit. So x is equal to minus negative 6, that becomes positive 6, plus or minus, and then the square root of negative 6 squared in brackets like this would be positive 36. Okay, and then minus 48. Okay, all over 6, 2 times 3. So now something strange happens here though, right? X is equal to, this is plus or minus, and we get the square root of negative 12 over 6. All right, you cannot take the square root of a negative number like that. So what's this telling us? This is actually telling us that there's no solution here. So in this case, there is no point. There is no maximum point where it changes from increasing to decreasing or the other way around. So yeah, so what this is telling us is that our function would be increasing all the time. So maybe that looks something like, it's going up and then continues to go up, right? It's always going up. So we don't actually have like a turnaround point. All right. So now how do we know whether or not it's increasing or it's decreasing, right? Because it's always going to be doing one. It's either going up all the time or it's going down all the time. So the best way to do that, like if this was our first derivative, let's actually plug in a number, right? It actually could be like any number, and let's see what actually comes out. So if we type in, maybe I'll change my notation here to be f of x, right? So maybe if I would have had like f prime of x, just so we can talk about putting numbers in. If I went f prime of 0, right? An easy number. Then if I put that in, that's going to be 3 times 0 minus 6 times 0 plus 4. Well, that's coming out as positive 4. Okay, so that means that it's positive. That's all I really cared about. So that means our graph is increasing forever. So we'll say f of x is increasing on and then it'd be from negative infinity to infinity. Okay, so now let's determine where the curve is concave up and concave down. So to me, with concave up and concave down, this is really a second derivative thing, right? Because, oh, let's figure that out first. Let's write the second derivative, and then we'll talk about where it's concave up and concave down. So if this was our first derivative up here, okay, well then let's find our second derivative. So that would be f double prime of x is equal to, and then this is pretty straightforward. This would be 6x minus 6. Okay, well, it's going to be concave up, right, when f double prime of x is greater than 0. Yeah, so just when the second derivative of f of x is positive, it's going to be concave up. So, and then here, I'll just write this over here right now too. It's going to be concave down when f double prime of x is less than 0. So let's just figure out where that's the case. So if this is our derivative, our second derivative, then let's say, okay, where is 6x minus 6 greater than 0? Okay, so then we'll just kind of solve this inequality. So we get 6x is greater than 0, or sorry, than positive 6. And then we'll divide both sides by 6 here, so we get x is greater than 1. So this will be the case when we're between 1 and infinity. Okay, so I did this as an inequality like this, right? And that worked out for us. The other way we could have done it is we could have made a number line with our critical numbers, and that would have worked as well too, right? This worked because we're only going to have one critical number, right? So it's going to be one way on one side of this, and it's going to be one way on the other side of it. So if you want to, like I said, the other thing we could have done, we could have wrote down, okay, where is this equal to 0? We could have went, okay, f double prime of x, is equal to 6x minus 6, and say, okay, where is that equal to 0? And that would have been 1 if you solve this, right? So that would have been 1. And then we could have tested, where is this thing positive on the left, and where is this thing, or yeah, what does this come out as on the left, and what does it come out as on the right, right? That would have been more like the last example, the way we did it. It would have worked fine, but in this example, I'm just doing inequalities instead, same thing. Okay, so hopefully that made sense. Okay, so now let's figure out where is it less than 0. So same thing. So this will be, okay, where is 6x minus 6 less than 0? So again, if you solve this, we get 6x is less than 6, and then x is less than 1. So this is saying that this will be the case when we go from negative infinity to 1. Okay, so that kind of makes sense, right? So now, let's find our points of inflection. You're probably guessing where this actually is. If it's concave down in this region from negative infinity to 1, and then it switches to concave up from 1 to infinity, really guessing that's going to be at 1, right? But let's just do this right. It's going to be where, right? We want to know where f double prime of x is equal to 0, right? That's where the point of inflection is most likely going to be. It'll only actually be that if it's concave one way and then the other way on either side of it, but this is what we should check. So this would be, okay, 0 is equal to 6x minus 6. We've done this calculation a few times. You'll probably believe me if I say x is equal to 1. Okay, so that's going to be where our point of inflection is. It's going to be when x is equal to 1. But it is a point of inflection, so we should find our y value too. So f of 1. So where is f of 1? So now it gets a little confusing with the first derivative and the second derivative. This is actually the function. So we want to know f of 1 of the original function, right? So if we plug in f of 1, you end up getting, for that first term, is 1 minus 3 plus 4 minus 5, and we end up getting negative 3. So again, that was just plugging in 1 in place of x for all of these. I skipped that, but I hope you're okay with that. So f of 1 is negative 3. So that would be, so I'll say therefore, this is going to happen at the point 1 comma negative 3. All right, so now let's use this to sketch our graph. All right, so let's sketch out a couple of interesting points here. And while it's on our mind, why don't we put this point down? We know that that's going to be a point on our graph. So we'll make one at 1, negative 3. So down, I'll say we'll put it down there. So 1, negative 3. I'd say another easy point that we can find would be our Y-intercept. And if you remember, our Y-intercept is going to be where our graph, where the constant number is on the end of it, right? So negative 5 would be our Y-intercept. So that kind of makes sense. That would be maybe down here somewhere. So that's going to be 0, comma, negative 5. And then we could factor this thing and figure out where our x-intercept is. I think we're okay if we don't, though. So we know that this will be our inflection point. This is just where it crosses the graph, is all that is. And we also know that it's going to be concave, so concave up from 1 to infinity, but it's concave down from negative infinity to 1. So it's going to be, I know I should have like a bit of a cup shape happening, right? Something like this from here to here, right? It's because it's concave down in that section. And then this is where it turns, right? So then it's going to turn and go back up from here. And that's probably good enough for our sketch.